Okay, now we're going to look at the third structure. Two horizontal metal plates are connected to a power supply as shown in figure 7.1. The separation of the plates is this much, the switch is closed, the voltage is 1.2 kilovolts. On figure 7.1, draw 6 field lines to represent the electric field between the metal plates. So they are specifically asked you to draw 6 field lines, which means that if this is the metal plate, then you have to divide this into 6 equal areas. 1, 2, 3, 4, 5, and 6. Right? The important thing is, if you haven't drawn 6, then you will not get any marks, because they are specifically asking you to draw 6 lines, and you should use the entire length of the metal plate. So you have to kind of divide the entire length into these 5 equal regions divided by the 6 field lines. If someone has drawn something like this, they have drawn 6 lines and they have drawn them with equal gaps. The gaps are equal and they have drawn 6 field lines, but they have left all the space empty, which means that more number of lines can be drawn there, right? Which means that the field of this one is stronger than the field that is actually there. So when they say 6, those 6 lines should occupy the entire length. So that's why in the mark scheme they are saying that there must be no area between the plates where an additional line or lines could be added. They are expecting you to use the entire length of the plates. When they calculate the electric field strength, the same kind of questions, just you divide the voltage by the separation, it gives you 3.0 times 10 to the power 4 volts per meter. So then the B part is quite beautiful and interesting. The switch S is opened and the plates lose their charge. Two very small metal spheres, A and B, joined by an insulating rod, are placed between the metal plates as shown in figure 7.2. Sphere A has a negative charge and sphere B has a positive charge, where E is the charge of a proton. So we know that E is 1.6 times 10 to the minus 19, but that is also given in the front page. The length AB is 15 millimeters, the length of the rod. The rod is supported at its center C. So at its center the rod is fixed. That the rod is horizontal and in equilibrium. The switch S is then closed, so the potential difference 1.2 kilovolts is applied across the plates. There is a force acting on A due to the electric field between the plates. Show that this force is 4.8 times 10 to the power minus 15 Newton. So we have already calculated the electric field strength, right? So if you want to calculate the force, the force is equal to, so electric field is equal to the electric field is equal to force over charge. So the force is equal to EQ. So the electric field strength we calculated in the first part as 3 into 10 to the power 4. The charge we calculated, it is given as the charge of a proton. The charge of a proton is 1.6 times 10 to the power minus 19 coulombs. So this gives you that the force is approximately 4.8 times 10 to the power minus 15 Newton. Okay. The insulating rod joining A and B is fixed in the position shown in figure 7.2. Calculate the torque of the couple acting on the rod. So now you see here, there is a parallel plate and the top is positive and this is negative. And if you look here, this is a positive charge plus C, and this is a negative charge, which means this is going to experience a force in the downward direction, which is the force that we just calculated, and this is going to experience a force in the upward direction, just like we are opening up a tap, right? So what will happen is we have a situation where there are two forces which are equal and opposite, but they are not on the same line of action, which means there will not be any translational motion, that the rod will not move like this or this, but it would simply start rotating, right, due to a torque or couple. They're asking you to calculate that torque. So first you must understand that couple is defined as one of the two forces times the distance, the perpendicular distance between the two forces, D. So one of the force, as we calculated, is 4.8 into 10 to the power minus 15 Newton times the distance between them is 15 millimeters. So 15 times 10 to the power minus 3. So this gives you a torque value of 7.2 times 10 to the power minus 17. The unit is Newton meters. Then the last part of that question, the insulating rod is now released so that it is free to rotate about C. State and explain the position of the rod when it comes to rest. Okay, so far the rod is fixed in the center and it was not free to move. Now only it is allowed to move. So obviously the part A is going to move like this, and part B is going to move downward, and it will kind of oscillate like this for a while, and then eventually it will come to rest, right? So when it comes to rest, it would obviously come to rest such that A is here and B is here, and the reason is then only the two forces will, the force on A and force on B will be acting on the same line and would produce no resultant force. So this is the alignment, and the explanation is the two forces will act on the same line, and when they act on the same line, the perpendicular distance between them is 0, so the couple or the torque is 0. In the question they are saying that the state and explain the position of the rod when it comes to rest. So in the question they are saying that it comes to rest. So if we now, there are two conditions for equilibrium. One is resultant force 0, the other is resultant torque 0. Now the two forces being equal and opposite implies resultant force 0, and they acting on the same line implies resultant torque 0. Okay, so your answer should be like this. First you should explain the position. So you should explain A would be at top and B would be at bottom, and the rod would be vertical, and because the two forces will be equal and opposite and would act on the same line, as there is no resultant force or no resultant torque.